Welcome back. So we were talking about MOS capacitors. Okay. We understood what is the physical structure of a MOS capacitor. Now let us see what happens when you apply voltage to a MOS capacitor. For that, I'll take this MOS capacitor and let's say I connect it to a battery. I'll apply some voltage. Let's call it VA. We applied. Okay. So what happens in this case? So remember, the semiconductor is having certain doping. Let's say we assume for a moment that it is p-type doped. Semiconductor is p-type. Okay. So what happens? So this is a 500 micrometer thick plate. Thick wafer, and we have made contact. We made good ohmic contact with the semiconductor. So there's no voltage drop across that. And then there is this oxide which is TOX, and then you applied a positive voltage on the other side. What do you expect? Okay. The moment you apply a voltage across a capacitor, there's an electric field which is developed, right? What is the electric field? The electric field developed will be, let me call it E oxide. Okay. E oxide will be simply Vox divided by TOX, right? Whatever is the voltage drop across the oxide, and then there is a TOX. But it really depends whether there is a voltage drop across the semiconductor. Right now, let's assume that it is small. Okay, it turns out that it's not true, but yeah, we will get back to it. Okay, so essentially, whatever is the voltage drop across the oxide divided by the thickness of oxide should give you the electric field across the oxide. Okay, so what happens if you have an electric field? What is the direction of the electric field? Well, it is pointing downwards in this picture. Right. The reason is the positive terminal is on the. We are assuming that the voltage is positive. So positive voltage is applied to the top, the metal, and let's say the substrate is grounded. So what should happen? So when you have an electric field in this direction, the semiconductor is p-type. It has a lot of holes. And what happens to holes when you apply voltage like this? They will be driven away from the interface, right? So what happens is, in this scenario, you are essentially, it looks like, if you apply VA greater than 0, what should happen is, you will have the oxide, and then you are applying metal. I can't show you the metal, but let's say, okay, there is a metal here. So essentially, it looks like you're putting a positive charge on this, and you're driving the holes away, right? So when you drive the holes away, you're going to get a region where there are no holes. And then what, if there are no holes, what should remain there? Well, doping, right? It's acceptor doping. When you drive the holes away, which are the positive charges, which are going away, then you will end up getting negative charge. Right? And that is how you're having the capacitor action. Right? And where is this negative charge formed? The negative charge is only formed under the gate. Right? You won't have any negative charge here. This is not possible, right? You only have, because there is no applied voltage on top of it. There is no capacitor action. The capacitor action only happens under the gate. Right? This formation of negative charge, I would say, is capacitor action. Okay. And how is this formed? Where is this charge exactly? It is actually distributed, right? Because it's a uniformly doped semiconductor. The charge is distributed across under the, depends on, how much voltage you apply. Let's say if your capacitance is, we can calculate the capacitance, right? In this case, C. By the way, whenever we talk of capacitance in semiconductors, we talk of capacitance per unit area, and that will be epsilon oxide divided by thickness of oxide. So I'm ignoring the area part of it. The regular parallel plate capacitor, epsilon A by D. A is the area divided by the distance between the plates. We will use capacitance per unit area. This will be having units of farad per centimeter square. Okay. So capacitance, and you apply a certain voltage, how much charge is going to be there, right? And if you apply a certain amount of charge on the positive plate, the opposite charge has to be uncovered in the semiconductor, right? The holes have to be driven away and you should have a depletion charge there, right? So this is basically the capacitor action leads to what is known as depletion charge. So this kind of a biasing mode is called as depletion mode. If you take a p-type semiconductor and let's say apply a positive charge, it's called as a depletion mode. You are depleting the substrate. You could have another scenario wherein you apply VA less than 0. When you apply VA less than 0, what happens? Well, you have the same substrate, and then there is an oxide, and then on top of it there is a metal. But now you are adding negative charge on the top. So that will cause the holes to come closer to the interface. So if you add a negative charge, what should happen in the substrate? There should be a positive charge. This is known as accumulation. This sort of a regime is known as accumulation mode. Okay. Remember, whenever we say accumulation, we are talking about majority carriers. They are free charges. Okay. These are free carriers or majority carriers. So physically, where will they be? They will be just under the interface. Whereas depletion charge is space charge. Or, I mean, if you want to call it, it's because of dopant ionization, right? Dopant, or, I'll call it charge or ionized dopants. So there's a key difference between the distribution of the charge in the semiconductor. Okay? It's not the same. It's not as simple as a parallel plate capacitor. If you have a parallel plate capacitor, where would the charge be? Even if I take, let's say, I'll take two pieces of metal. Just one moment. I'll just give me a moment. All right. So we were talking about the depletion and the accumulation mode. And we said that if you have a negative voltage applied on the gate, so by the way, the metal is called as a gate. Okay? And if you apply a negative voltage on the gate, it will create accumulation of carriers in the substrate. This accumulation or depletion is dependent on the type of the substrate. So far what we looked at was, if you consider a p-type substrate, and then I'll have an oxide, and then I'll have a metal. Okay, so this I'll call as a gate. Okay, so essentially the gate voltage is controlling the type of carriers. That's why we call it a gate. Okay, so now if you have this substrate, you could also have an alternative structure wherein you start with an n-type substrate, and then apply. There is an oxide. This is oxide. And then there is a metal on top, which I'll call as a gate again. Okay. So let's change our notation a little bit. Now what we have seen is, if let's call this as gate voltage VG. Okay. If you apply gate voltage which is positive, greater than 0, then if you have a p-type substrate, you are going to drive holes away, and then you get to depletion regime, depletion mode. Okay, wherein you have space charge in the substrate. Okay, so this is distributed over a certain distance. We are depleting the semiconductor, p-type semiconductor, and so there will be a uniform doping, let's assume. Then you will have a charge profile which is distributed in the p-type semiconductor. And if you apply Vg less than 0, you have accumulation. Accumulation of the majority carriers, which are in this case holes. Okay, and these are located right under the Holes are right under the interface. Right, I think I was talking about this just before the break. So what I was trying to get at is, let's say if you have a metal, a simple parallel plate capacitor. Let's say you have a parallel plate capacitor consisting of a metal of some millimeters, another metal. Okay, this is simply the thickness of the metal. Okay, let's say this is 1 millimeter, and this is another 1 millimeter. You have the separation. Let's say it's again, 0.5 millimeters, just for explanation. Okay, so now if I apply voltage to this is a simple parallel plate, capacitor. Okay, so where, if you apply voltage, where will the charge be? Okay, the charge, let's say if you have positive charge here, there should be a negative charge. But where will the charge be physically? It will be at the edge of the metal, right? Because we know from basic electrostatics that there cannot be any charge there cannot be any electric field in the metal, right? Electric field is zero. Electric field equal to zero inside metal. Outside, non-zero. So at the interface, there has to be a charge, which is going to be plus Q, right? So this is at the edge. Similarly, in the other plate, there will be a negative charge, but that is right at the surface, not inside the metal itself, right? What happens in a p-type, this sort of a, if you have a semiconductor which is p-type, when you deplete it, the negative charge is not really at the surface, but it's distributed within the p-type semiconductor. And if you have accumulation, it's right at the interface. Okay, we will draw some space charge diagrams, and this will become clearer. Okay, but I think this is not very difficult to imagine. All right. So you have this for a p-type semiconductor, and when you have this sort of a configuration, we will call it as a NMOS capacitor. It will become clear why we call it. Okay. So if you say an NMOS capacitor, we are talking about a p-type substrate. Okay. I can also have a n-type capacitor, n-type substrate, right? If I have an n-type substrate, what happens? When my gate voltage, Vg, is greater than 0, what happens in a n-type substrate? Well, gate voltage is greater than 0, so I'm going to have positive charge on the gate, right? Gate has positive charge. So the substrate should have negative charge. Where will the negative charge come from? Well, there are lots of free electrons, right? N-type semiconductor has lots of electrons. So you'll end up getting negative charge at the surface. If I have this sort of a structure, this is your N-type. And then there is a oxide, and there is a positive charge on this side. So when you apply a positive charge now, this has become accumulation of electrons. This is called accumulation mode. Whenever you accumulate majority carriers, when you have extra majority carriers, it's called as accumulation. And if you apply Vg less than 0, what happens? Well, Vg is less than 0, then the gate has a negative charge, and that will repel the electrons away from the interface, and you have depletion. Okay, if you have this case, sorry, my space is going smaller and smaller, but essentially what you have is, so there's negative charge on the top gate, and then on the semiconductor side, we have space charge, which is distributed slight distance away from the interface. Okay, so now we are depleting the semiconductor. Depletion mode, I can call it. Okay, so you have two types of modes. One is accumulation mode, one is depletion mode. It depends. If you have a N-type substrate, we call this as a PMOS capacitor. PMOS cap, so N-type substrate. PMOSCAP and NMOSCAP. Okay, and the behavior is exactly opposite. For an NMOSCAP, if you apply a positive voltage, you get accumulation. Okay, sorry, if you apply positive voltage in an NMOSCAP, you should get depletion. If you apply negative voltage, you get accumulation of holes. Right? And if you have a PMOSCAP, if you apply a negative voltage, then you have depletion. If you apply a positive voltage, you get accumulation. Okay. So this is the simple picture of what's happening. Now we would like to understand a little bit more depth. We will want to talk about band diagrams. I'll do that in the next video. Thank you.